Ladies and gentlemen, welcome aboard Imperial Airlines flight number AE2215. Please can I have a moment of your time as I go through the L2 application's design procedures. Please ensure that your wind turbine has been printed as a single part, that is a horizontal axis design, that it spins at a maximum of 3,000 RPM, and that it is in fact a turbine and not a propeller. When the seatbelt sign illuminates, this means you procrastinated for too long and you should now start the design process. First, draw up the hub. Design the turbine around the specifications of the hub. Tighten and adjust the size of your nose cone as needed. Make sure the wind turbine has been designed to rotate clockwise when viewed from the direction of the wind. It also should have a TSR of between 3 and 8. There are several restrictions on the printing of the turbine: the length, the width, and the height. Please take a moment now to locate your nearest 3D printer. In some cases, the nearest 3D printer may be behind you. We wish you all an enjoyable time. Thank you.
So, now we know what the objectives and constraints of the project are. Let's design this thing.
The first thing we had to decide was the number of blades, and we decided pretty early on that our turbine was going to have 2 blades. Why? A one-bladed design would be the optimum number when it comes to energy yield. However, one blade could cause the turbine to become unbalanced, making it impractical in reality. Similarly, 2 blades can potentially offer greater energy yield than 3, but would be more prone to a phenomenon known as gyroscopic precession, resulting in blade shattering. Naturally, this wobbling would cause further stability issues for the turbine and cause it to wear down over time. Commercially, a 3-bladed design is used as a compromise between efficiency, long-term structural integrity, and stability. Given the short time scale of the project, 2-bladed design did not come with any significant drawbacks, while making it easier to print, increasing structural stability, and reducing the potential for unpredictable effects that could be present in more complicated designs.
Next, we have to determine the chord distribution of the turbine. Theory dictates that the circulation around the blade must be constant for maximum efficiency. Circulation is a function of velocity, incidence of incoming flow, as well as the airfoil geometry. However, this presents a problem. Imagine this ruler is a turbine. When I rotate it, the area around this part of the ruler moves a much greater distance than this part of the ruler. This means that the resultant velocity and incidence of the flow changes along the length of the blade. To keep circulation constant, the chord and twist of the blade must vary along the length. Thus, we use the Schmidt chord distribution and modified it near the root of the turbine for structural reasons.
An initial tip speed ratio, defined as the ratio of the tip speed to wind speed, was decided as 4.5 because, well, it was simply close to the middle of the range and not too far from the optimal TSR of 2 pi. Given this, Reynolds number could be calculated, which allowed for extensive research to be performed on different airfoil sections using the XY data. Ultimately, SG6043 airfoil was chosen due to its unmistakably superior CL over CD characteristics that did not result in a big trade-off of structural integrity.
So now we know the chord distribution, the airfoil, and the TSR. So what do we do next?
The radius!
Yeah! For our initial conditions, a radius of 30 centimeters and a hub radius of 2.2 centimeters was arbitrarily chosen. To perform calculations for the optimal radius, the blade was discretized using 51 points into 50 panels, and the flow velocity at each of those points was calculated.
At each of the previously discretized points, the Reynolds number was calculated to assign the optimum angle of attack for the best CL over CD ratio. The twist angle at each point was then determined using the Schmidt's formula.
We then had to ensure that the blade did not fail catastrophically and make a huge hole in the new expensive wind tunnel, which meant that it was now time for structural calculations. Lift and drag were calculated for each position of the blade. Given this, the resultant force at each point of the blade was calculated and resolved in the wind and rotational direction, which allowed for total torque calculation.
Power output and CP were calculated using the torque produced by each section.
Using the cantilever approach, a series of repeated Simpson's integrations were performed to find the moment distribution and subsequently the maximum tip deflection. Through the obtained moment distribution, total stresses can be calculated, which allowed us to iterate over many different blade radii, finding the optimal radius given the yield stress of ABS plastic. The radius that should theoretically produce the largest CP without failure was found to be 23 cm, which was slightly larger than the printing constraints.
In the pursuit of perfection, we decided to try a radius of smaller than 20 centimeters and found that, even though there was a small reduction in the predicted CP, the large decrease in total mass would still result in a desirable performance index. As an additional benefit, this resulted in an easier design as no hinge mechanism was needed. After much debate, we chose a simpler design and with a final radius of 20 centimeters.
As the blade was smaller, the TSR needed to be adjusted, so the angular velocity does not go over the maximum value of 3000 RPM. A TSR of 3.5 was picked. Ultimately, however, a TSR of 4 was predicted, given the likelihood of an underestimate from previous year's results. Using bending theory, a maximum deflection of 5 mm was calculated.
To further optimize the turbine as well as add a personal touch to it, we decided to create a channel section inside the nose cone that should help deflect the flow towards the blades. Additionally, winglets were added to reduce induced drag at the blade tips. As the trailing edge of the airfoil was too thin, a circular shape was also added to the trailing edge of the blades to ensure proper printing and also to ease the sanding process. And our design was done. Now let's make this thing.
The manufacturing was split into two parts: the manufacturing of the aluminium hub and the actual turbine. The hub was manufactured in 4 steps. First, the surface of a cylindrical block of aluminium was smoothed out to achieve the desired diameter using a lathe. A 16 mm diameter hole was then drilled at the center. Next, it was fitted on to a CNC milling machine and the block was cut into the hexagonal shape. And finally, a 3-meter hole was drilled on one of the faces so that it can be secured to the testing rig. Next, our turbine was 3D printed in the longitudinal direction based on our CAD file. Finally, the turbine was then sanded as smooth as possible to reduce skin friction for a laminar flow.
Finally, it is time to begin testing. The tests were carried out in the T2 wind tunnel. Our turbine successfully started at 10 meters per second and was able to run at wind speeds all the way from 6 to 12 meters per second. However, the produced power and CP were very small at 6 and 8 meters per second. Luckily, as the wind speed increased, so did our power and efficiency. And our turbine produced a peak power of approximately 20 watts at a wind speed of 12 meters per second, which corresponded to a CP of 0.149. The TSR of this power output was 3.9, which was very close to our predicted TSR of 4. This means that our calculations and assumptions were mostly correct.
What about the nose cone channels?
Oh yeah, had completely forgotten about those. To test the channels, we used some tape to cover all the holes to test the turbine again and investigate the effect of those channels on performance. And there was essentially no difference in the power output or efficiency. What? To understand what was going on, we used a smoke streamline generator to visualize the airflow around the nose cone. As you can see from the footage, the channels did not perform as intended and no airflow was directed towards the blades. We think that this was because the channel was too small and not enough airflow was passing through the channels for the smoke to be visible.
If we happen to fail this year and have one more chance of building a wind turbine under the same constraints, we will likely stick to our 2-bladed design, but there are a lot of improvements that can be made. There were 4 main adjustments we could have made in our design, all of which were because of our reluctance to take massive risks.
The first adjustment we would make would be to the nose cone and the hub, which could have been modified much more carefully by implementing a mesh design instead of printing it solid and drilling holes into the hub to reduce the mass. Another design feature, which had too large of a safety margin, was the large cord at the root, which contributed to the drag. We could sacrifice the structural integrity for a more aerodynamic design. Since our turbine radius was very small, the trailing edge was too thin and couldn't be printed. Thus, we had to add material to the edge to be sanded later. However, in the end, our fear of breaking the turbine resulted in very badly sanded areas and an inaccurate trailing edge. To solve this problem, we could increase the thickness of the trailing edge by slightly increasing the turbine radius, such that it can be printed accurately. The last improvement is adjusting the channel to have a larger diameter at the opening, which would have been much more ideal in effectively diverting the flow, along with an added benefit of reducing the mass of the hub.
So now you know how a group of 5 wannabe aeronautical engineers designs a wind turbine from scratch in 5 weeks. We hope you enjoyed this video and see you next time.